Okay, so with that, I'm excited to introduce our last keynote speaker of the conference, Dr. Moira Chas. Moira earned her PhD from La Universidad Autónoma de Barcelona in 1998, and she's currently an associate professor at Stony Brook University with research interest in low-dimensional topology. And today she's going to tell us about Lie algebras related to curves on surfaces.
Okay, well, thank you for inviting me. Before I forget, I would like, would it be possible maybe somebody could be my chat helper? I concentrate in one direction and I don't see chat, and I really would like to encourage anyone who wants to ask a question, feel free to do that. And I know some people feel more comfortable with chat, but I need somebody to tell me when there's a chat, okay?
Sure, I can do that for you.
Okay, I hire you then. So, and please, this should be for learning something. And, I just wanted to crack the door open in this topic that I find marvelous. I want to add that I also researching now in math history. As a little advertisement, there's a woman called Alicia Bull who's absolutely fantastic, and I'm working on her life, so I open myself to new avenues of research. And this is what you see on your screen is my plan, which is incredibly ambitious, like impossibly ambitious, I would say. But let me start, because otherwise I wouldn't do anything at all. So first, I want to define this fantastic structure in curves on surfaces, which is the Goldman bracket. So let me start to, say where that this bracket lives. So here, well, we have a surface, and let me see. Can you see? Oh, let me just point with my mouse. You can see. Can you see my mouse? Good. So pi, I'm going to call the fundamental group of the surface, and pi 0, and we'll have a reason for that, is the set of free homotopic classes of directed closed curves on the surface. This is just, the curves on the surface up to continuous deformation. It's a set. And I thought, sorry, let me just start over. I had this very nice build-ups that are not working. Oh, I'm not presenting. That's why they're not working, because I'm not making them work. Okay, now it's good. Sorry, I'm starting over. So now we're looking at curves, and you're looking at curves up to deformation. And the way I like to think curves up to deformation is there's this movie inside, the picture where the curve moves to another position. This is equivalent to have that you map a cylinder where one boundary goes to one curve and the other boundary goes to the other curve. You can do that continuously. These two curves are freely homotopic. So this is our set. This is the, one of the protagonists of this talk. And another homotopic we can look at, I pinch this cylinder here. I join this point with this point. And I'm going to, it's still, I can factor this map to that. So if I map these two curves and, these curves here, we can see these two are freely homotopic. Here, this curve that I mark here that goes along the cylinder, I squash it here to a bit fat point. And here is another example, a little less silly, of two curves that are freely homotopic. So this suggests that if my curves have a base point, which of course I said it doesn't, but let's just take curves, passing through certain points, you can see that when two curves are freely homotopic, say A and A prime, there's another element that conjugates them. And in fact, this can be, right carefully, and you have that this set that we're studying is in one-to-one corresponded to the conjugacy classes of the elements of the fundamental group. So now, I'm just to remind you, we have the fundamental group, and I emphasize the word group in boldface and red, and the word set in boldface and red. And the reason I do that is because, well, here in the fundamental group, we have an structure that, we all know and love, I'm sure. And here, a priori, there's no structure. I mean, there's no way to define an operation, and, much less with identities, but we're going to do it soon. So we're going to define a structure in the algebra. If you read the title of the talk, in the linear combinations of elements from this set. It's just a formal basis that we're choosing. And the coefficients are in any ring, I think I will switch between R and Z and they will not make a difference for what we're doing today. So for instance, if you have two elements, the A and the same curve with the opposite direction, this is not an identity that we have. These are just formal elements. And in the same way, the trivial loop is just another element of my basis. These are just like subindices. You can think of them as elements of your basis. And just for why I calling it pi zero, well, if I keep going forward, I might arrive here, but this pi zero is not pi zero of the surface. The pi zero we know is pi zero of the free loop space of a surface. So this is a set of connected components of the maps from the circle to our surface. And I might be able to say a little more about that. Okay, now we arrive to the definition. So, if you're going to learn something in this talk, maybe this is one good moment to learn something. So if you're sleeping, wake up, and maybe I should yell and listen. So I want to define a linear algebra here in this model, of vector space if I use R instead of Z. So what I want to do is, well, I have a natural basis of free homotopy classes of curves. So if you give me two free homotopy classes of curves, I want to give you what is the bracket of these two curves. If I define it in the basis, I can extend it by linearity and I'm done. So let's define in the two elements of the basis. So here I have one representative of one class and one representative of another class. And they have two intersection points. I mark them there. So I'm going to define one term for each intersection point. And this is a moment where you could object, because if you give me two random curves on a surface, maybe they intersect in uncountably many points. So how am I going to define it? Well, I'm going to prohibit that situation. So I'm going to choose two representatives that intersect in transversal double points. I don't know if you can see me. The intersection is like this. These are my intersections. I'm not allowing any other intersection like that. That is not like that. And it's always possible to choose a pair of representatives that do that. So now I have finally many intersection points. And as I said, I'm going to give you a term for each intersection point. So I have two terms, a red and a purple. And what I'm going to do is let's define I said red and I pointed the green. This happens to my brain sometimes. This green point, the term will be, just start at the green point. So I had to give you the term. What is it? It's a number, a sign, a number, and a free homotopy class of a curve. So what is the free homotopy class? Well, I'll give you a representative of the free homotopy class, and it's the curve that starts here, goes around, the light blue curve goes around, comes back, and then goes around the blue. So what I just did is a standard loop product, the product that we do in pi 1, you go first around one loop and then I go around to the other loop, but and then I take the free homotopy class. And this can be seen as, well, I replace this little, picture like the cross by these two, the little surgery that I did there. And then I'm going to put a sign to each term. If you want identities, you need a sign. And the sign comes from comparing, here I have two, I have an ordered set of curves, the light blue and the blue. And the light blue, I see a tangent here and there's a tangent here. These are directed curves. So since they are ordered, these two tangents define an orientation of the surface. First the light blue, then the blue is an orientation like this. This orientation in this example coincides with the orientation of the surface, which I should have said, I wrote it, but I didn't say explicit. I need a surface with an orientation. So if it coincides, we put a plus. Now I do the other one, and I did again the same surgery in the purple point. And here it has a minus, well, because the blue is in the same direction, but the light blue goes in the opposite direction. So it has to be not the orientation of the surface. And here I have, yeah, this is something that is important. So I use, fanfaria. So the bracket, notice that it combines two structures that we know very well. One is the intersection product from the fundamental group. Sorry, one is the intersection product of sets, the nice sets, intersect sets. This is transversal intersection. And the other is the loop product, the product of the loops in the fundamental group. We're putting them together. So if you have two free homotopic classes, a priori, doesn't make sense to say multiply them, but now we go to each spot where we can multiply, we multiply and we add all the terms. Any question? So I repeat because this is the definition, it's important and beautiful. So, and I'm the boss when I give you the talk. So here it is. This is the example. And the magic theorem, which was written by Goldman, is that this bracket is well-defined, skew symmetric, and satisfies the Jacobi identity. And I didn't want to put this. I want to ask you, what is the first thing we have to do? And, well, notice that I choose representatives. So every time you choose representatives, you have to pay the price by proving it's well-defined. So, and notice though the fact that it's well-defined is already a mathematical miracle, but it satisfies the Jacobi identity. Skew symmetry comes because I put the sign using the order of the curves. It's very easy to see, but the magic thing is the Jacobi identity. So we're going to see it. But first, let me convince you that it's well-defined. So here is a very quick idea. So say that we have two curves that are, A and A prime are freely homotopic. I want to see that if I bracket the same curve with A and with A prime, I get the same bracket. And this is just with an example. So we have two curves here, the light green and the dark green. And we can see that this, I marked the intersection points. The terms corresponding to these two pinpoints, these are equal. They are the same, when I compute them, they are the same free homotopic class with the same sign. I'm intersecting with these two curves and comparing. Now, there's three terms here, 1, 2, and 3, that correspond, that those, if I compute them again, they're all the same sign, even regardless of the orientation of the surface, and same free homotopic class. And then this one gives also, the yellow point gives the same free homotopic class, but opposite sign. If you look at it, hard with passion, you probably see that. So then, when I sum these three terms, well, these two cancel. I think I have the picture here, and you get same bracket. Now, the proof in general is quite similar to what I just did, just generalize. And here we're using again the magic word transversality. It's another important character in this show. Here I have two curves, and I want to prove these two curves, the blues are freely homotopic and the red are freely homotopic. And now, well, I don't want to use any homotopic for these proofs. I want to get a homotopy, which is nice. And what do I mean by nice? I'm moving both curves simultaneously through the homotopic, and the curves, there will be a few spots, more than 6. These are just the 3 types of spots where there's no change from, this point to this point in the two curve, except on a disk on the surface. And what is the change? This is a little disk on the surface. Well, this picture here changes to this picture. Same here and same here. So now, why can I do this? Well, because basically, you can guess in the middle of these two, there's going to be a tangent point, A tangent point, the two curves are tangent, is something that happens very little. So we can think of them as walls in the space of curves. And every time you have a wall, it's a codimension something, you can transverse that. And so I make sure that every wall I transverse, and then if I manage to prove that at this point is the same as this point, since the structure doesn't change except for this little disk, I will be done. And this picture here is the same that we just observed in the previous example. You know, these 2 points are going to cancel, this and this, the bracket corresponding to these 2 points. And here one could see, well, one has to see, you know, put orientations and do the cases, but basically this point is the same as this point, and the signs are going to work, and same with this. So the bracket is well defined. And you may ask, you know, why are you putting this point? This has no impact in the bracket because it's a self-intersection. Well, the reason is I'm using transversality and I'm just eliminating all this weird stuff. So this is something that weird that happened. The structure of intersection changes. That's why I put it there. I need to transverse all the walls to make this. Any question? I talked a lot without, no? Okay, so now here is a question that I often heard when I discuss this. You know, if I put an example like this, people say, wait, aren't those representatives the same? You know, are those representatives freely homotopic? So what do you think? They could be. Nobody says they are not. You know, this I'm taking the representative of this curve here and this the green point and the purple point. Anybody wants to bet? Are they freely homotopic? You can bet in the chat. It's just a game, okay? I'm not testing you. Yes or no? Only young people can answer though, not David. Nobody answers? Just, oh, there's a chat, okay. I think no.
A few no guesses.
Okay, no. Everybody said no. Well, somebody should say yes, so I can tell you no. Yes, no, you're totally right. It's a no. And yeah, these two terms are different. And you know, I'm going to give you a little sketch of the proof. So this one, you know, if I call this loop A, so this is A, and then I'm going to call this loop C, and then this is B, so this is ACB, and this one will be ABC. And let's think this, what I'm saying, what I should prove is the conjugacy class of one is different than the conjugacy class of the other, if the claim is true. So here is a picture. And what does it mean that these two things are homotopic? Let's suppose they're homotopic. So I have a cylinder, this is a cylinder with a property that one of the boundaries goes to this one goes, this is like this. This boundary, the outside boundary goes to ABC, the inside boundary goes to ACB.
Moira?
Yep.
Sorry to interrupt, but I wanted to ask before you got far away. Those two curves, you might have said this, I had to step out. They should be inverses in the algebra, are they? Are they like sort of inverses under that Goldman bracket, those two curves?
What do you mean inverses?
If you took the Goldman product of those two curves in the top right, then they would be like a contractible loop, maybe?
No, I don't understand, sorry. Repeat it slowly.
If these two curves you have in the top right,
these two curves, these two, yes.
If you took their Goldman product, would
yes,
that
the
be
Goldman bracket of one with the other?
Would that be a contractible loop, like the trivial thing?
I don't think so.
Okay. Well,
I should check, but you know, I strongly doubt it.
I just wondered if that was like how you, yeah. Okay. No.
It could be, I mean, a bracket could be 0 too, you know, if these two terms were the same, no, it's not. So but thank you. Oh, sorry. Oops. Sorry, my coffee spilled. Give me 1 second. I spilled all the coffee. And I learned the painful way that iPads and coffee are not a good combination. Okay, so now, and I moved my thing. So here we have a homotopy between the outside curve and the inside curve. So this means this circle goes to, you know, say that this curve, whatever it is, ABC, and the other one goes to ABC. And there's a homotopy. And the homotopy is colored. And what I'm coloring is each point with the color of the surface they land. Okay? So this is what it has to be. I mean, this is a schema of the picture. Notice that each, for instance, here the green, there's a little bit of yellow inside, and you know, every time you go from green to red, there's a yellow. Okay, so now if you have something like this, maybe I can use a tissue. It would be like, you know, like I'm going to look the outmost loop. This is a sentence that we all like very much. This is the innermost loop, this one here. So this is like, if this is the yellow thing, here I have like a finger, you know, this is in green, this is the yellow, and this is the inside. And I can always push the homotopy out. So I'm going to do that, check the magic of, you know, Keynote or PowerPoint. And now look at my homotopy. I can keep doing that until my homotopy looks like this. And now, if you see, what I have is this is the base point. This curve here, which is a power of C because it goes around the yellow thing. So this curve here is equal to, well, first do B, then do a power of C, and then do B minus 1. And I think I wrote it here. So this tells me that, yeah, there exists M and N so that a power of C is the same as a conjugate to another power of C. And this is not commutative because, you know, you see, you know, M and N are not the same, but it goes in that direction. And surface groups are not free groups, but they're almost free. You know, they're very non-commutative, and this cannot happen. So then this is not possible in a surface group. Any question? I don't know who talked before, but well, hopefully this clarifies. If not, please, please, please keep asking.
In that relation down at the bottom, that's a relation in a fundamental group pointed
Yes.
here.
This is in the fundamental group. Absolutely, yes.
Where is it pointed in order to make that relation?
In the blue point.
At the blue. Oh, I see.
Right. It's a very big point. Yes. Yes, that's a very good question. Thank you. Any other question? So, I mean, I think, you know, sometimes pictures are good. This is a good picture to learn too, you know, the idea of a homotopy pushing, and we push it back and the inner loop. So if you want to register in your head, take a screenshot of in your mind. It's a good thing to do. And if you are bored and you want to compute things, you can compute the bracket in the torus. I can give you homework.
In that last picture, was there any bracket like in the discussion at all, or was that all about the whether or not those two conjugacy classes are identical?
No bracket here.
Yeah, okay. Got it. Thank you.
Okay. So as I said, you can compute the bracket, you know, in the torus in several stages if you're bored, and, you know, I can test you at the end. I can take a quiz, but let's move on. Now, let me just put this. So I'm presenting. So now I'm going to prove Jacobi. And for that, let's start with 3 curves. I'm going to look at one example. So these are here, I have 3 curves in my surface, and I'm going to take the bracket of the 3 corresponding classes. So I'm going to represent, you know, these 2 circles together, red and blue, as this is just the sum over the points. This is a representation. So the red and the blue intersect in point P and point Q. So I just put right here P plus Q. This represents that sum. And this sum represents the sum of the pairs, you know, a pair here, a pair which the first point is here in the red blue, and the second point is here in the green red. Okay. So for instance, you know, so this is, you know, P clue, and this is PT, you know, like PT, PU, etc., etc. Okay, now this is, we call it sometimes stone algebra. Oh, so one point, you know, if I want to compute one term of the bracket, and this is the image inside my head is like you have these two chosen points. In this case, they are P and T. So as usual, you know, you're going to race around and you reconnect. But the way I look at it in my head is, you know, so here I have P and T. you start and you stand in any curve, in any of your curves, and you are driving a little car in the direction of the curve, and you move, say here, move here. And the first time you arrive to one of your points, so here I arrive to T. And there, instead of going straight, I have to turn in the direction of the arrow. So here the arrow goes like this. So I have to turn, and then I go around. And then I arrive to P. And when I arrive to P, I turn and I go around until I come back to P, and then I go back again. Anyway, every time you're going to ride, you have to do a couple of turns, and then you will back to the same point, and that's a turn. So then we can represent the bracket. We have to prove that this triple sum is 0. So the bracket of red and blue is the sum over the intersection of the red and blue, the intersection points of the red and blue curves, and which is represented by this. If I bracket this with a green, well, now the green can either intersect one point in the red or one point in the blue. And again, this is a sum over pairs, each of the things. So I do the same thing for all of the cyclic permutations of ABC, and look at what happens. Well, here I have red in the middle, and here I have red in the middle. These two are the sum of over the same intersection points. So if I go in my little car, and I have to turn, the free homotopy class will be the same, because the pair of points only tells you where to turn. So I get the same free homotopy class. And now if I look at the sign, well, here I have red, blue, green. And here I have the red is before the blue and the red is before the blue. So here there's not going to be weird sign attached. But when I do red and green, so here the red is before the green, and here the green is before the red. So these two are going to have opposite sign. Therefore, these two are going to cancel. And if you see it, all the pairs are going to cancel, and here you have Jacobi identity. And again, now, remember that we started with the set of free homotopy class. We took all the linear combinations, and in this, say, vector space, we find a Lie algebra structure. In that is, a little mathematical miracle. So I just want to appreciate that. So let me just try to relate this with the intersection of curves on surfaces. So let me remind you that if you have two curves, two free homotopy classes of curves, the intersection of the free homotopy classes is the smallest number in which representative of the class can intersect, and you always request that they intersect, in transversal double points. So here, for instance, in our example, the green class and the red class intersect in 2, because you have to find the minimum. And of course, you could argue, oh, well, maybe these points, I can deform my curve so they cancel. Well, you have to trust me. After all, you invited me to give a talk here, so they don't. You can, it's not hard to see that they don't. The free homotopy classes of these two are different. So now I'm going to, let's look at our well, in this case, it's a model, a linear combination of elements of the free homotopy classes. And if you take an element there, it's an integer times a class, integer times class, and so on. This is a basis, so I'm going to request that, I choose all elements of the basis different. So the L1 norm or Manhattan norm of this is the sum of the absolute values of all the coefficients. In some sense, what I'm doing here is I'm counting how many terms are up to sign. And I want to see how this relates to the intersection number. And just for having an example, in the bracket of the two curves that we computed in the beginning, the bracket is this, and the Manhattan norm is 2, because the coefficient 1 is 2. If, which didn't happen, but if these two terms cancel, the Manhattan norm will be 0. And it could cancel, maybe. So I claim that the Manhattan norm of any pair of free homotopic classes is smaller or equal than the intersection number. And why is this? Well, because, take two classes of curves and now choose representatives that intersect in the smallest number of points possible. You can do it with any representative and, transversal, of course. So then if you compute the bracket there, you're going to have as many terms as intersection points. So therefore, in your first computation, you have as many terms as intersection points, but you choose it to be the minimal. So that's it. The Manhattan norm of that will be exactly the minimal. But maybe I should have put it here. Remember that what I said is that, well, we have to write, to compute the Manhattan norm, we have to write it as an element of, the standard way you write something in a vector space or model. So you don't want two elements to repeat. And you could have things that cancel in your free homotopic class. So you produce the cancellation and then you compute the Manhattan norm. So here, the question is it equal? Can I have cancellation? Any bet? I'm looking at the chat now. Any bet? Is it equal, not equal? Come on, say something. Don't see like it should be always equal. Okay. No. Okay. Yeah, well, you are very good. For some time I thought it was equal, and at some point I wrote down a program to compute this bracket and surfaces with boundary, and I discovered that it's not, like you have to compute examples, it's not. So here is an example. So this example is equal, for instance, and here is an example where it's not. So here I have two curves. This is a pair of pens. And there's two intersection points, green and yellow. So what is the term corresponding to the yellow point? So you go to the yellow, and then you have to first go around to the first curve. So the first curve, I didn't say, but it's the red. It's not going to change it. So it's, you go A. So you go around, A is just going around this boundary, and do A, and then you do B, and come back to the yellow. And now you go through the blue, and so you do B, A. So this is A, B, B, A. And then you do the same thing with the other point, and you get B, A, B. And well, this is, these two are conjugated. If you conjugate by A, you get from this, you get this. And if you look at the signs, they are different. Here I have the red pointing in this direction, and here I have the blue pointing in the same direction as the red. So the signs are different. So therefore, the bracket is 0, but the intersection point is 2. So the question is, well, one is equal. Well, Goldman proved that, if you know that the bracket is 0, meaning that the Manhattan norm is 0, and one of the classes does not intersect, has a member that doesn't intersect itself, one of the classes is simple, then the two are disjoint. So in some sense, this equality between M and I that I wanted to hold, it works under restricted circumstances. Then I proved that this also works with intersection number. That if one of the curves is simple, then the bracket does count intersection. The reason why behind this is, one of the questions that I like a lot in math is, you're given an algebra, you have some topology and you define some algebra given that topology, and then you look at the algebra and you say, what can I recover from the topology? That's where I might try to go. So here, if we know about the things about the intersection of curves, you know a lot. So that's my secret goal. And here is a little bit of the proof. I'm going to skip. I was going to talk about it. The reason is very similar to the one that we discussed with these two curves were not conjugate. It works on that line, on those lines. This is something I don't know. yeah, so if you have a simple curve, then this is an equality. But you know, if we don't know that is every simple curve has another curve which is not going to be simple, whose Manhattan norm is smaller than the intersection. That's something that is open. And all of the things I checked, you know, with computer programs, but you know, it takes a long time. I mean, I can do up to only finally many things. So there's still hope. I think it's true though. Here is, well, how can I find self-intersection? I want to determine when a curve is simple. And when a student of mine, we worked, if you have a surface with boundary, and you take the bracket of x and x bar. You know, in fact, today in the breakout room before, we talked, let me just mention something. We talk about mistakes. So I am a big admirer of this Goldman bracket and of Goldman and his paper. I think it's beautiful and deep, and it's also incredibly full of, you know, a lot of interesting things, including this bracket that I found marvelous. But at some point he was proving something, and he wrote, oh, even then if you computed the bracket of a curve and the same curve with the opposite direction, clearly from the picture it follows that you get 0. And you know what, I realize now I didn't do it. I'm going to stop doing this, and I'm going to do it. Let me do a picture of this, because and let's just do an example. So say that I have you know, let's just do it. It works in any case. I'm going to do it with a curve that intersects once, but it is going to work exactly the same. So let's take this curve. And let's take the same curve with the opposite orientation. So here it goes like this. And let's call, you know, say this loop is A. So you go around here, this is A, and you go around here, let's say this is B. So we are bracketing, say the blue, which is A, B, and this is the free homotopic class, of course, with AB or BA. Let me just write it BA because I want to be like, you know, it's conjugacy class, but anyway, these are the class of these two elements of the fundamental group. So these two curves intersect in 2 points, here and here. So if I want to compute the bracket, well, here, let's see, I need help because here I go like this. No, yes. So the bracket will be, the bracket corresponding to this point is A, B. So I do A, I go down the blue, and then B, maybe let me mark it. I'm pointing, but of course you can't see because A and B. And now I have to do, I have to go around the red curve in the direction of the red curve. So this one is, notice I go A bar and then B bar. So this is A bar, and I write, sorry, oh, this is my private notation. I use capital letters. So this is A bar, A inverse, and this is A inverse, B inverse. I use capital because I put this in the computer, and you know, it's much easier to put capital letters than bars. And then the next one will be, and I'm going to just write it, BA, BA. And these two, you know, yes, the one class is the opposite of the other in direction, but they don't cancel. You know, they are two different terms. And in fact, so just these two never cancel. But if you have more intersection points, you know, if you have a curve that intersects a lot, it turns out, and I should have put this, it turns out that M, I mean, and this is experimental, not proven, M of X, X bar the number of terms is 2 times the self-intersection points. Let me tell you, the number of crosses, the minimal number of crosses self-intersection of X. Here, my curve intersect once, and the M is 2. Well, in general, it's twice. And I tested this for an enormous amount of work, curves. I can do curves up to a certain, curves are represented by word, and I can do up to a certain length. And this is true. And I'm working now with my collaborator in India. I hope he's okay. And, we almost have it. He thinks we have it, but, he's younger, so we don't have it completely written. So, I mean, I think we are almost have it. But this, I've been trying to think about this for decades. And in the midst of this, so since I couldn't prove in the beginning X and X bar, what I prove is X and X cube and X and X square, and this also counts self-intersection. And later, with Siddhartha Gargil, we proved that, well, one way to count intersection and self-intersection too is if you take powers of your curves that are large enough, then you can intersection. So, there's powers here between, there's P and Q large enough so that, the Manhattan norm is equal to that. And this is this is hyperbolic geometry. Let me see the time. I may do the proof of that. I have to decide what I'm not going to talk about. I'm thinking. Maybe I'll skip this piece. Maybe I'll do it, which it's the, yeah. Let me talk, and if I have time, I'll go back here. I just wanna, because we just finished the Goldman bracket and I have 18 minutes. So I wanted to talk about, how this got generalized to string topology, and I'm going to skip some of what I promised to say. So if anybody's desperate to hear about the bracket of unoriented curves, you can yell now or shut up forever. Not forever, until the end of the talk. Okay, no complaints. Okay, so we were trying to find, I was working with Dennis Sullivan, and we're trying to find how to prove many things related to self-intersection and this Goldman bracket, and the dual of this Goldman bracket, which is a derived co-bracket. These algebraic structures on spaces with, this basis of free homotopy classes. And there was a statement that looked marvelous, and we thought we had to prove it because it's so pretty. If a curve, if something is 0, one of the things is 0, the curve is simple. So we try and try and try. And we never were able to prove it because, well, the thing was false. But in the midst, we started to study families of curves, and then, string topology was born. So, when we've computed the Goldman bracket, we have a surface with an orientation, and then we compute linear. We're going to define a linear bracket in the space, in the model with basis free homotopy classes of curves. So now, well, if I have to generalize this, and again, this was born organically when we were not really trying to generalize it. We were looking at, imagine that, you have two pairs of curves that are homotopy inside a surface, just this is one pair in my hand and this is another pair. And I want to have a homotopy between this pair and this pair. So my curve is moving, like I'm moving in a homotopy. So I have to follow a homotopy, my curves are moving along the surface. And then that gives you a family of curves, well, a homotopy is like a family of curves, and we have to follow continuously. And this is how we start to find, homotopy. And in each point of the family, you look at the intersection, and then you do the product. So the way to generalize these families of curves was the equivariant homology of the free loop space, which I'm going to, say a few words in a second. And the parallel is as follows. So here, and remember that I said, I call it pi 0 because the pi 0 is like the zeros equivariant homology of the free loop space. It's like the connected components of the free loop space. but I'm not taking, the loops are like my points. That's the idea. I mean, I take it kind of more up to the cyclic action. So now, to define the bracket, our method was we start to representatives that they are in transversal position, you intersect, and you product and sum. So what we're going to do is now we're going to take two families of curves, two cycles in this homology, and we're going to take representatives of these cycles that intersect transversally. Now it's no longer in points or not necessarily. And then when you intersect two cycles just as manifolds, imagine that I intersect two submanifolds, I get a cycle again. And now I can orient that. And then at each point, this cycle has a loop of one family and a loop of another family, so I can multiply, and I have time to go over this again. And then I'm going to obtain a family, and that's the bracket. And again, the keyword here is transversal. Transversality is what is underneath all these ideas. So very, very briefly is like, basically what I'm going to take is the loops, up to the cyclic action, but I have the contractible loops or the loops that go to a point. So that's a fixed point of the action, and I want a quotient, but I don't want to, have, I want to have a nice space. So I'm going to make my space, my loop space, nice. But so my action, free by taking the Cartesian product with a space that has a free action, and now I'm going to take the quotient, and that's the homology. And you just, easier to think, if it's easier to think of the loops as points in the common sense way, it's fine. So so here is the loop space. As we said, the zeros homology is just the set of it's a set of free homotopic classes in some sense. But if I take homology, each connected component corresponds to a free homotopic class, because going from one loop to the other, it's a homotopy. And then the homology itself is just the direct sum over each element of, whatever is generated by that element. So whatever is your ring here. So, now, what is H1, like the one families that I mentioned? Well, we can think of these one families, these are cycles. So this is like a torus of loops. This is a foliated torus, it's divided on loop, and I map it to the manifold. That's my one family. And this is, this is a typical element. I mean, it's a linear combination of this is an element of this, my H1. And let's just look at, I'm going to make the bracket with these two types of elements. I could keep going. I could take 2, 3 families, 4 families, but I'm going to stop there. So let's make the bracket now with a 1 family and a 0 family of curves. So I map, representative of each to the manifold. And now since I have, and of course, I wrote there a 3 manifold, I should have said it. Since I'm in a 3 manifold, and I request transversality, this, a curve and a surface intersect in points, and finally many points because I'm requiring transversality. So now I have these 2 points, and notice what happens. In this point here, I have the loop, which is the closed curves, and I also have a loop of the family that is highlighted in light blue. Same thing for this point. So the bracket is defined by, as we did before, go to the points where you can perform the loop product and perform it. So there it is. And then you need signs, and this is, you're going to orient every object you have here, and you're going to compare that with the orientation of the manifold, and that will give you, well, in this case, it's a sign. The orientation of the point is a sign. So let's look at the next one, which is more interesting. So now imagine that I'm mapping a torus. This is a torus that is divided into foliated torus to the manifold. And here, well, this is a piece of my torus, okay, in light blue. I couldn't draw it all. And this is the curve. And again, these two things, oh, sorry, I just did that. No, I'm not going to repeat this. I don't know why I put the repetition. Let's put two tori. So these are two fiber tori. And here I make them, intersect transversally, and they're going to intersect in finally many circles. And again, in each point, if you look at, I look at two circles, here I have the green and the yellow. This point here has one loop of one family, I'm going around it, and one loop of the other family. So at this point, I can multiply. At each point of the green circle, I can multiply. Then I'm going to orient the green circle, again, using the orientation of the objects I have and the orientation of the manifold. And that's a new cycle. But if I, to this point, this green circle now is going to be like a parameter space of my new family. And then the loop I attach is go around this and go around this. So this is again a new torus, because I'm going to perform this and take the family, and this is, I will get two tora in this particular example. And long time ago, we proved that, this is, and I put three manifold, this holds for any oriented manifold, any orientable manifold. So this is well-defined and satisfies Jacobi. And the proof of Jacobi is the same proof that we saw before. And well, it's nice, this is just, this one, because we just saw that if you take, one families and one families, you get one families. So this is a Lie algebra itself, and this is a Lie model. If you apply, an element H0 tensor H1. And in general, so, when you have a family, so if you have a family of dimension I, and remember a torus is dimension 1, so there's a confusion always because a torus, a fiber torus, is a one family, it's a family, one-dimensional family of loops. So when I say an I-dimensional cycle, if I look at the image, this is what I'm doing, I look at the image of this cycle, the loop, in my manifold is going to have as a submanifold, if I want to look at it that way, if I can, it's going to have dimension I plus 1, because it's the dimension of the family plus the loop around. If I look at the whole thing as a block to intersect them. So what I'm doing is I intersect an I plus 1 thing and a J plus 1 thing in a space, and if the space has dimension D, when you intersect an I plus 1 and a J plus 1, you get the sum of both minus the dimension of the ambient space. So it's I plus J plus 2 minus D. And a very reassuring fact is, like, if you look at it for the surfaces, is 0 plus 0 plus D, which is 2 in the case of the surface, minus 2 gives you 0, which is good. And again, here, you can check that this gives that. Sorry, I kept talking and I didn't let anybody ask anything. Any question? I lost everybody? Okay. And now I look at the clock. I could do some examples. So here, just to see pictures, we can see one example here. So let's take an easy manifold, which is a surface cross the circle. And the way to represent the surface is with boundary. This is like a disk with 4 holes. So we're going to glue just nicely, this top part with the bottom, identified in some way. So now, if I have, I can think of two families. These are one families of loops, and I check in how they intersect, and then so when the curves, that the bracket we study will help us to see the places where these two things intersect, and then again at each point, oh, sorry, I'm pointing, I forget, gosh, I need to be in person. I'm pointing my iPad and doing things that you can't see, and I forgot. So here at each point, again, you have in one loop from each family, and this is when you multiply. This here and this here will be the parameter space. So this, here I have another example. This is a more realistic one than the one I put before. Here I have two tori that go inside and out, and and how they multiply. And I'm going to, well, maybe I'll just mention this, and then I might finish. I'm have a discussion with me in my head, because either I have too little or too much to say. So remember that we were studying that the Goldman bracket, it's a linear combination of homotopic classes, and then we can study how the bracket encodes the intersection structure with the Manhattan norm. Well, it turns out that there's something similar with the string bracket, and I have another collaborator in India with whom we are finishing this, hopefully some point. We've been finishing for a lot of years, but I think we are almost done. That we can use, the string bracket can tell you things about the three manifold. In other words, if you know what is the string bracket, you know something about the three manifold. What do you know? So, well, oh, sorry. Well, let me just stop here. I can't say it fast, and I don't want to take too much, but so you can invite me again and I'll talk about this.
All right, then let's all thank our speaker. And if anyone has questions, you can feel free to unmute or put them in the chat.
So has anybody thought about what happens when you lift these Goldman brackets to covers?
Yes.
What happens?
Well, I mean, this is one part that I skipped. Let me just show you one picture. So here I have, maybe I'll show it to you. So this is, here I have these two, and imagine that this is a torus with a boundary component. And imagine that I'm going to consider two geodesics. So, I can do nice pictures this is the universal cover here. So I'm going to lift the two curves, with this base point, the intersection point. So now, if I want to look at the term, well, imagine that this is a lap of the curve from here to here. This is a lap of the blue curve, and this is a lap of the red curve. So this is going around completely both. So once I arrive here, if I want to lift the product, I mean, I just can do the product by going straight and turn, so, well, how would it look like? Well, here I have to grab, a lift of the blue that passes also through this point, because this point is the same as this, and then you're going to keep doing a zigzag. So when you lift the representative, the product, as soon as you just multiply the two geodesics and then lift, okay? You're going to get a geodesic with an angle, it's a quasi-geodesic, a fake geodesic. And then, you just have this thing. And in fact, it turns out that the representative, the geodesic representative corresponding to this term is exactly the curve that passes through the middle of this zigzag curve. And
by middle, yeah, this is a picture of the universal cover that we're looking at?
Yes.
And when you say middle, do you mean like in a metric sense, or?
Yes, so these are the middle points. So this is the intersection. This point here I'm pointing, and this is a lift of the intersection point that you're studying. This is the midpoint between these two.
Right.
Yeah. Right. So, and it passes through all these mid. So you have a zigzag, and yeah, this is the middle, passing through all these midpoints of these the geodesic segments that form them.
Oh, that's really surprising.
Yeah, and then, it's really nice. Well, I like this. What can I say? Because
right? And so that
yeah.
that always ends up being a finite sum of closed geodesics on the.
Say it again.
So that, if that's the lift of the
One term. Yeah, this is one term.
one term. Okay.
The term corresponds to this intersection point.
Yeah. I mean, a priori, I don't really see any reason why that would end up projecting to anything, closed geometrically. So that's super surprising.
Well, let's see if we see any reason. Well, I mean, in some sense, it's not crazy because I'm telling you that it's passing through these points, which are the midpoints. So I'm going through this midpoint, and this is the same midpoint.
Oh, I see. Yeah.
But
Okay.
But there's a lot of, no, you're onto something, because there's a lot of things you can do with this. With these ideas now, and we are writing about it. Yeah, there's nice definitions you can give of the bracket, and this length, for instance, this is one lap. So this thing is one lap of the curve. But if I go from here to here, this is the full left. This is the midpoint again of this geodesic. So this is half of the length of one curve. This is half of the length of the other one, and this is the angle. So with the cosine formula, you get the length of this one.
Yeah.
And then, for instance, one nice thing that we use later on is that, well, suppose you have two terms that cancel, two terms of the bracket that cancel, and you look at the geodesics. Well, it turns out that the angles at the turn, if you put a hyperbolic matrix always, the angles of these 2 points have to be the same, have to be congruent when there's cancellation.
And so you picked a metric in order to draw this picture, but does this mean that it's consistent, relative to any choice of at least negatively curved metric?
Constant negative curve.
Yeah, sure. That's cool.
Yeah.
Moira?
Yep.
I was going to ask, sort of in a naive thought process, you showed this is like a Lie algebra. Is there, and you showed that, if you take really large integers, then the Manhattan distance of the product of the powers is the product of the intersection, the powers and stuff. Is there some sort of notion of like exponential map of these things, sort of like thinking of it as a Lie algebra? And like, say if you iterated, like say you took a curve and then iterated this product of itself a lot of times, would this somehow fill up the surface in the sense like, you keep product bracketing the curve with itself. Let's say it's non-simple. And then so it kind of starts cutting itself into lots of pieces, and those pieces can all, say, land in some component of pi 0, and therefore you've kind of like filled up the surface in some sense.
Well, there's something that, this is an indirect answer, but, Feng Liu, a long time ago, he discovered this very nice operation, which, on simple non-separating curves. I'm taking another example. You said non-simple, I'm saying simple, but bear with me. So he said, take two curves. If they intersect exactly once, you multiply them and you use the orientation to multiply them in certain way. These are unoriented, but you can orient them, it doesn't matter. So the thing is, he proved that all non-separating curves are finally generated with this operation. And this is what the bracket does. So in other words, if I start with a set of finally many simple curves, I will be able to generate all simple curves because his operation is covered with the bracket. So I'm guessing that yes, but that I don't know if with two, but with finally many, it will cover everything.
Does that work for every mapping class orbit?
Every mapping class element?
Orbit.
Well,
I
I didn't.
guess, yeah, sorry. That doesn't
Right. Yeah.
Are there any other questions for Moira? Okay, if not, then let's thank her again. Okay, and that is going to bring an end to our conference.